This interview is part of the History Heard project. The content of this interview may be used for historical research. However, no part of the video itself may be reproduced without the express written permission of an authorized History Heard representative. Today is July 19th, 2012 at 3 p.m. This is an interview with Dr. Richard Gatti in Los Angeles, California. He was born on January 12th, 1937 in Hoboken, New Jersey. Dr. Gatti is a distinguished professor of pathology and laboratory medicine with a specialty in human genetics at the UCLA School of Medicine. His research focuses on molecular genetics, cancer genetics, immunology, and DNA repair with the long-term goal of developing gene-based therapy and improved diagnostic testing for patients who are at an increased risk of cancer. Dr. Gatti, would you please explain the kind of research you do in layman's terms?
Well, we do a lot of different kinds of research, but basically I've been exploring a disease called ataxia-telangiectasia, which we call AT for short. It makes it much easier for everyone. For over 30 years now. And we basically started by bringing together a critical number of families so that we could then locate where the gene was in the genome. Mm-hmm. And that led to the cloning of the gene. And then we moved on to characterize all the different types of mutations that can occur in that gene. Mm-hmm. The first thing we found is we confirmed that there was only one gene. That's very important because we were expecting more than one. But there's only one gene for this disease. And now what we've been trying to do is figure out how mistakes or mutations in that gene cause the patient to end up in a wheelchair for the rest of their lives and develop cancer and all the other things. And recently been trying to correct some of those mutations with drugs that induce the ribosomes in the cell to read the RNA in a more liberal way, let's call it, mm-hmm. so that it reads through certain types of mutations called stop codons. Mm-hmm. And it basically is like going through a stop sign. You just don't stop, you keep translating. And that produces a certain amount of functional protein that we hope will correct the disease. Mm-hmm. What we've also found out along the way is that this approach can be used not just for AT, but for just about any other gene where there's a mutation. Oh, wow. So we're working on drugs now that could transform the world of genetics and especially the clinical world, where at the moment there's no really good treatment for it. An inherited disease, you're stuck with it. Mm-hmm. Well, this would be the beginning of a new era where we can treat the mutations.
That's incredible. What have been the major breakthroughs you've seen in your field since you've graduated from medical school?
Oh my goodness. Many. Just to give you one example, all of immunology is based on the idea that stem cells in the body are like students going to a university. If the university is closed, there's no reason for the students to be there. They're not going to learn anything. Mm-hmm. If the university is non-functional, it may not be closed, but it may be under siege or something, the students are still not going to get educated. Mm-hmm. Some of the diseases that we've worked with over the years are called immunodeficiency diseases. And part of the problem is either that the stem cells are missing for some of those diseases. Those would be like there are no students enrolled. Mm-hmm. And the other would be that the university is closed, and that is there are patients that are born without the thymus gland in the neck. Mm-hmm. And the thymus is where you educate your T cells, and without a thymus you don't make T cells. beyond a certain very rudimentary stage that they don't have much function. They don't know what to do at that stage. So they're really like uneducated students.
Mm-hmm.
And what I've seen is when I went through medical school, they had no idea what the thymus did, nor that the center of immunology was based on the thymus. And in another gland that is not really even defined, in chickens it's called the bursa of Fabricius. So we have T cells for thymus and B for bone marrow or bursa, depending on how you want to remember it. If you work in chickens, there's no problem because there is a bursa. In humans and other mammals, there is no bursa. It's an organ that we either no longer recognize or we've lost it through evolution. But the function is clearly in our bodies somewhere. But maybe it doesn't look like an organ. Maybe it doesn't have a sac or walls, but we certainly have B cells, and they seem to mature in the bone marrow. Fortunately, they both begin with B. So they're B cells and T cells. None of that was known when I finished medical school. Mm-hmm. We went on to do the first bone marrow transplant in 1968, and I had no idea where that would lead there's the boy right there. That's the first successful bone marrow transplant. And next to him is his sister. She's the one that we took the bone marrow from.
Wow.
I did that with a friend on a Saturday morning in Minnesota in 1968. Well, those are some of the changes, but there have been so many changes. Even in the past 10 years, and genetics is just, every month you read the American Journal of Human Genetics is a new, shocking, revealing change, just breakthroughs that rearrange your thoughts after you've read this discovery.